Hello, hello, hello. Let's see if we can. Hello. Advanced audio properties. 15. Hello. Okay, my volume seems pretty good. All right, so here is the Ben Eater clock module with just the astable 555 here. So what we have here is basically just to go through the pins. Pin 1 is ground. Pin 2 is I forget. Hold on. So pin 2 is the trigger, which the trigger probably goes to the S in the SR latch. So that's why we I'll need to pull up Firefox here. Okay. I know it's not like the best view, but let's just look at this. So what we're going to be doing is building the monostable part of this, and basically recreating his video, but just like in a worse way, I guess. So let's just switch over to this. And why is my... Wait, what? Wait a minute. This makes no sense at all. But did that change? Okay, good. I don't know how that happened. That's a weird bug. Okay, so, but also my screen capture is wrong. Yeah, OBS on Linux is actually pretty bad. Yeah, I just don't know how it's so bad. Okay, but it seems like everything is working now. So, so the threshold and the trigger are tied together with a cap to ground. Yeah. And then right, because we want the two comparators to be at the same okay, so that checks out. Alright, so now we're going to be moving on to the... So here, I have this program actually open, and what we're going to do is demonstrate bouncing in this little push button circuit that I have wired up. So I need to go get a resistor. Oh no. Yeah, outdoor electronics is kind of a pain because of the lighting, but it'll be alright. So I have this push button here, and the idea is to I'm just gonna go get a resistor. And then I think I didn't bring the LED. So I'm gonna go get a resistor and an LED. Okay. So we have a resistor and we have another LED. Okay, now what we're gonna do is, I always forget, does the long lead yeah, okay, so the long lead goes to plus, so we're gonna do this, and then we're gonna just have a current limiting resistor. It goes like that. Okay, so now this is working. So now if I press this button, can you see that? Okay, it turns on. So that's good. But what we're gonna do is we have an oscilloscope probe here. So I have an oscilloscope and I'm gonna plug it in like this. And then I'm also gonna plug it into the negative lead of the thing. Okay, so now should be able to press the button like normal. And what we're gonna do is we're gonna switch over to this program called waveforms. Okay, so you see how our voltage is at 4 volts. Now if I do this, but we need to set the trigger. I wish the trigger would just figure it out, but it never figures it out. So if we set our trigger at 2 volts, it'll come centered. So do you see how much it's bouncing? I wonder if I can record. So see how many times it bounced? So if we're trying to drive our computer, we got 1, 2, 3, 4, 5, 6, 7 pulses, or six or 7 pulses. So that's really bad. So that's where this next video for the monostable comes in.
So in the last video, we used a 555 timer here to build this little clock circuit. And so we have our pulsing clock output on pin 3 of the 555 timer. And we can control the speed using this potentiometer. And so that's great, but there might be times when we want to manually control the clock. And we want to be able to just push a button each time we want the clock to advance or we want our computer to advance.
So, okay, so he motivates it with the button.
Clock pulse. So this now is a 555 circuit that is going to happen once. So you definitely want to get rid of that. And so this now is a 555 circuit that is going to help us with this switch bouncing problem. And so, well, before we get into it, let's just try it out. Let's push the button and see what happens. Push the button, the light comes on, and then a little while later the light turns off. And importantly, what happens if we...
So let's try to figure this out. So trigger is pin 2. So this is at VCC. This is at V. So this pin 2, the trigger should be high. Let me get a pen. Is this the bad pen? I think this is the bad pen. Okay. Wait, we can just actually, I remember, we can just go to... Oh my god, these angel number, bro. That's insane. How many times have we looked at this angel number thing? Alright, so this is what I wanted to look at. So trigger... So this trigger should be high, right? If we were to measure this voltage, it would be high. Which means that this is low. So S is low. But then when we press the button, this is going to go low. And this is going to get set. So this is high.
We push the button multiple times, and the light only comes on once, and that's what we want. And this is called a debouncing circuit. And there's a lot of other ways to build debouncing circuits, but I'm using the 555 timer just because I think it's a fun chip to play with. And so the timer here that's controlling how long this stays on when you push the button is controlled by the resistor and capacitor over here. And so
that's 6 and 7. So 6, right, it just so happened that we tied these together, but you can make them different. So 6 is with a capacitor, and it's tied to 7, which is discharge. Okay, so by default, and what is 5 at? 5 is not even hooked up. So, but internally 5 is hooked up to VCC. So 5 is going to be high by default. And the threshold should be high as well, right?
Yeah, you remember before we had 2 resistors and a capacitor that were controlling the pulsing. Here we just have 1 resistor and a capacitor, and we'll go into more about how it works. But basically, the time that the LED stays on is just, you pretty much multiply.
Give me a second here. Okay.
Multiply the value of the resistor times the value of the capacitor. And so this is a 1 meg ohm resistor, and this is well, it's a 2 microfarad capacitor. It says 1 MFD on it, but apparently these are 2 microfarads. But anyway, the nice thing about this is 1 mega ohm is 10 to the 6th, and microfarads are 10 to the minus 6. So the math works out really easily here, so that a 2 microfarad capacitor, when you multiply it together, you just get 2. And so that gives us a 2-second delay. And sure enough, we push the button, and the LED stays on for 2 seconds, which I guess is further confirmation that this 1 MFD capacitor is really 2 microfarads.
So wait, so what's going on though? So this is tied to a resistor to 7, which is tied to ground. So there's a resistor out here to ground, and it's tied to this. So this should be low, which means that the reset should be high.
Anyway, so 2 seconds is kind of long for what we want. So what we could do is we could put in a 0.1 microfarad capacitor instead of this 2 microfarad capacitor. And if we stick that 0.1 microfarad capacitor in there, that's going to give us 0.1 seconds. Because we're multiplying it by this 1 meg ohm resistor. So now it stays on for 0.1 seconds. No matter how quickly I push it, it's kind of hard to tell. But that's what we want. We want it to pretty much follow what we're doing when we push the button. But we critically are getting rid of those bounces. And so as long as any bounces that happen within the first 100 milliseconds or 0.1 seconds, we've gotten rid of. And that's what we want. And so I understand how this works. Let's look again at our circuit diagram. And I've got the 555 timer here, the guts of it exposed here. But the green bits out here are our circuit. And of course we have an LED hooked here to the output. I didn't draw, but and of course we're just looking at this lower half here. This is what we built in the last video. And so we've got our resistor here, which is our 1 meg ohm resistor. Then we have our capacitor, which is a 0.1 microfarad capacitor. And then
Yeah.
And over here I've got the button hooked up, and if you look at how this is hooked up.
Oh yeah, that's tied to, no, that's tied high. I thought that was tied to ground, but that's high. So this should be high. And this will charge up so that this is high, right? Because it's before the capacitor, so it'll charge up. But Q naught gets asserted when we hit our trigger. So when this goes low, this is going to flip on, turn this off. This capacitor discharges. But S is going to get asserted. S is going to get latched until this point at 6 and 7 gets below this 3.3 volts here. Okay, I feel like this actually makes sense.
Button
This
is
is not
connected
that
between
complicated.
ground and pin 2. And then it's also from pin 2, you can see we've got a 1K pull-up resistor. Basically what that does is it ensures that pin 2 is normally connected to 5 volts, but then when we push the button, it connects it to ground, and then pin 2 goes to 0 volts. So just like before, we've got this voltage divider network going on inside the 555 timer, and so we've got 5 volts up here, and then we've got 3.3 volts here at this first point, and then we've got 1.667 volts here at the second point, and then of course ground is at 0 volts. And so that's just a voltage divider,
right.
Resistor voltage divider. We've got 1/3
So this is all pretty simple.
is off, and that's going to, that must mean, that the Q output of this SR latch is off, and so the inverted Q output must be on. And so if that's on, then that's going to be putting current into the base of this transistor. And so this transistor will switch on and will be discharging, or will be pulling current through this transistor.
I think I might have had it backwards, actually. It's kind of flipped though, because in here, okay, let's just see what he says again.
At the second point, then of course ground is 0 volts. And so that's just a voltage divider, resistor voltage divider. We've got 1/3 of our voltage, 2/3 of our voltage, and then up here is our full voltage. And so we can see right now, our output is off. The LED is off. So if our output is off, then that must mean
Right. So that means that reset was asserted, right? Because this is off.
That the Q output of this SR latch is off, and so the inverted Q output must be on. And so if that's on,
I did have it flipped.
Then that's going to be.
So this is draining. So 6 is low. Okay, wait, I gotta be back in a second. Okay, so I did have it backwards. So the reset
output is off. The LED is off. So if our output is off, then that must mean that the Q output of this SR latch is off, and so the inverted Q output must be on. And so if that's on, then that's going to be putting current into the base of this transistor. And so this transistor will switch on and will be discharging, or will be pulling current through this transistor. And so, in this state right now, current is flowing, from our voltage source through the transistor to ground. And if this capacitor had any charge on it, that would also be, discharging to ground. And so this capacitor doesn't have any charge on it, and so our threshold is at 0. And of course, 0 is not above 3.3, and so this is going to be off. And then this down here is 5 volts, right? So it's trigger pin.
Right. Okay. So what we're saying is that R has not been asserted, because you don't need to assert R, because this latches the data. So right, in this case, I'm not actively clicking on either of them.
Two is 5 volts, and 5 volts is not below 1.6 volts, so this is also off. So both of our S and our R inputs into our SR latch are off right now. And so somehow this latch is just latched into this state where it's off. But what happens when we push the button? When we push the button, we now pull this trigger low. We pull this to 0 volts. And so 0 volts is definitely below 1.6 volts. And so this comparator here turns on.
Okay, so it's not like the time to discharge. It's the time for this to fill up to be greater than 3.3. Because what happens is this is going to short to ground. This becomes 0. So then this turns on. This Q hat turns off. So now charge is going to flow from the VCC through the 1 mega ohm into this 0.1 microfarad capacitor, filling it up. And that charge is an exponential, you could call it decay, but it's really decay to its set point, to however much charge it can put on there. Or I guess is it decay to VCC? I'm pretty sure it's decay to VCC. So then it's going to, once it passes 3.3, this is going to automatically get asserted, but it takes time for this capacitor to fill up. So that's really what's happening.
The set of our SR latch. And so that turns the output on. And so sure enough, we push the button, the output comes on. So no surprise there. But the other thing that happens is when that output comes on, this turns off. And so we're no longer, pulling current through this transistor here. And we're no longer discharging this capacitor. So instead, we're charging the capacitor. And we're charging the capacitor through this resistor. And so this capacitor is going to charge. It's going to start to charge. And eventually, it's going to get above 3.3 volts. And so when the capacitor charges to above 3.3 volts, now the reset is going to be triggered. This comparator is going to turn on. It's going to trigger the reset. And that's going to turn off our output. And it's going to turn on our inverted output here, our inverse Q. And that's going to push us back into this state where we're now discharging the capacitor. And now there's no resistor between this capacitor. Remember in the circuit before we had another resistor in here, but there's no resistor here. So this capacitor is going to discharge immediately. And so it's just going to drop right back down to 0 volts. Which of course is going to immediately turn off this comparator, right? Because 0 volts is certainly not going to be above 3.3, and so this comparator is going to turn off, and we're not going to be triggering this reset anymore. But if we're not pushing the button, we're not triggering our set anymore either, and so the latch is just going to stay in its latch state, and our output will be off. So
yeah, I guess that's part of the phase that it. So. So this part's shorted to ground, so this is 0, so this is just gonna be low, and it'll just stay low, because this current, but since 1 mega ohm, it's not like you're drawing a lot of current. Okay, that checks out to me, so I think it's time to build this thing. So let's switch back over to here. So we're going to use this 555. And I'm sort of just going to copy down what he has. I'm not really all that interested in getting it perfect. We are going to turn off our power though. And alright, so we're going to put the button in. So I don't have, the best button. I like those buttons that bridge across, but we don't have them. I think they're coming tomorrow. All right, so we're gonna put this on 14. Okay, let's move this guy over here. Okay, so we're gonna move this 14, and actually wait. Here's what you should do. And one other thing I'm going to do is cut these long leads off. Okay. $14. Okay, 14 and 16. Now we have our button set up. Let's get the oscilloscope out of the way while I do the wiring of this thing. Okay, so we have wire here. And the next thing that we're going to do is we're going to put in our 555 timer at position 16, 17, 18. Okay. Now we're going to put in our from 20 to like okay. And then we need this is probably just another 220 ohm, so I'll probably need to go get those. I put those away. And then now let's add. Alright, so here's the tools of the trade. We got our cutters and then our needle nose, or our strippers. Okay, so then what I'm going to do is tie this pin. Actually, you know what? We messed this up a little bit. Let's do it like this. But we can do this after. So let's put this like right here. So this is going to go from here. So let's. Okay. And then he said count 3 longer than you want. So we want it to go to there. So 1, 2, 3. Okay. You can pull this out. I don't know how he does this so easily. This is not. I'm going to strip off more. Okay, it's not as beautiful as his, but that's okay. Alright, now we need to take. Now we just need our normal ground. We basically just need to power this thing. It seems kind of long. I'm going to do it a little bit shorter. I'm actually going to try to make a mark here. Oh yeah, now that feels nice. That's correct. That's how you're supposed to do this shit. Okay, so now we have this. Now we need to power the other side of it. Okay. So now we have the power. We have the switch. We just need the 1 mega ohm resistor. And then we need the, so there's going to be a resistor here, and then there's going to be another ground pin here. Perfecto. Okay, so now we need our resistors. Yeah, actually, I have an idea. Hold on, I'll be right back. Because, yeah, I need capacitors too. I need resistors and capacitors. So let me just go get that. Or let's put in this green one too. So this is between pins 6 and 7. Let me put it right here. One thing that I like to do is I like to take this and crush it, because then you can get it a little bit easier in there. Okay, let me go get some resistors and capacitors. Okay, so I have the. I didn't get the electrolytics, but he's replacing it anyways, so I got these. And then I have the kit with all of the most common values in bags. So we need the mega ohm. And then I can just always replenish these bags. But it's annoying to have to keep going back and forth, but what am I going to do, electronics inside? Am I crazy? I do need to sort them. I didn't sort them. But we'll sort them later. Let me just find the mega ohms. There we go. So we need 2 of these, right? Let me just and then this one, this is from the output. Yeah, this is just the output. So we can just put this. Okay. So that's the current limiting resistor. Now we want, what is that? Brown, black, red. Wait, I thought he said 1M.
So, you remember before we had 2 connected to 5 volts. But then when we push the
If you guys look up the old mnemonics for remembering these, the Wikipedia page has some of the most insane. It showed up on my suggested searches or my search history. Anyways, they used to be naughty. 100. So 2 zeros plus 5. Wait, 2 zeros plus 4. 2 zeros plus 4 is 6. So this is a 1M. All right, so whatever. He said 1M. I'm going to trust that it's a 1M. Switch it back over. Okay, the sunlight is not particularly helping me right now, but it's all right. So what we want is that the button is attached to high. Okay, great. So I think we have most everything, right? We just don't have the 2 sort of critical parts to this. We need our 0.1 microfarad and then Oh yeah. Okay, so for a four band resistor, these are 5 band, but this is also 1M. And this is going to be tied to pin 7, which is the discharge. And it's going to be tied high. So pin 7 is tied high. And this is bridged. And then now we just need a 0.1 microfarad. Okay, so what we need to do is we need to tie this to ground. So this needs to come like way out here like this. So what I'm going to do... Should I make this a little bit nicer? See if that's wide enough. Oh yeah, that's perfect. There we go. And then pin 5. Okay, so this should just work. Alright, so let's... Oh, the light is terrible. What if I... How could I shield this? See it a little bit better. Can't see anything. Let me look on my phone, see if you can see it on my phone. Wait, why is this here? Nah, you should still be able to see the light. Okay, so what we're going to do is we're going to turn this on. This one's flashing. Okay, so now what we want to do is we want to hook it up to the oscilloscope. So did you see the light turn on? Yeah, there you go. Let's go to waveforms. Well, actually, let's tie it to pin 3. I feel like this isn't... Should we zoom out a little bit? So let's try changing it out for a much bigger capacitor, right? I can't even hit it fast enough to... Alright, so the biggest that I have here is a 10... Okay, so we have our bigger resistor here. Let's turn off our power. take this out. Okay. Nope. Whoa. Okay, that should be good. Actually, I don't know. Let's just do this. Just gonna do this. Oh wait, I did this. It'll still work. Should have given a little bit more room though. Okay, hypothetically, this should now turn on for a long time. Okay, there you go. Wait, do you see that? It actually went on for so long. Okay, cool. Alright, so we see the same behavior. Oh yeah, because that was 100 times longer. Alright. Anyways, we want the debounce of this, so let's just do that. We can take this one out. I actually save all of these. Not that I've ever actually gone back into the bin where I have these all, but you know, you never know. Okay, so we've now built the sort of second stage of the clock, which is very cool. So now we're going to go into the third stage of the clock, which I believe that's the rest of this whole video is just that.
Connects it to ground, and then pin 2 goes to 0 volts. So just like before, we've got this voltage divider network going on inside the 555 timer, and so we've got 5 volts up here, and then we've got 3.3 volts here at this first point, and through this resistor. And so this capacitor it stays on while the capacitor charges up. But then once the capacitor gets to the 3.3 volts, boom, our output goes off and it just stays off. And it stays off until we hit that trigger again, until we push the button again. And so you might hear this referred to as a monostable mode of the 555 timer, because it's called monostable because there's one state where it's stable, and then if you push this button, it goes into this other state where it's not stable, where it's going to, eventually this capacitor will charge and then it'll drop out of that state. Whereas the, what we did in the last video with this is called an astable multivibrator or astable mode for the 555 because it doesn't have a stable state. It's constantly altering between two states on and off. So you might hear those terms, monostable and astable. So to take a look at that in action, I've hooked it up to the scope here, and I've also gone ahead and put the that 2 microfarad capacitor in there again, just so we get that nice slow 2-second pulse there. So if we fire up the oscilloscope here, push the button, you can see the output goes immediately high, and you can watch the capacitor charge, and then boom, as soon as it hits that 3.3 volts, so let's see, 1, 2, 3.3, yeah, 3.3 volts, capacitor gets there, and boom, it just, that discharge pin flips, and the capacitor just instantly discharges, and then of course our output turns off then. And so you can see any bouncing that the switch is doing in here, doesn't matter, our output's already high, we've got that latch that's latched it high, and then, as long as this capacitor will just charge away, and then boom, turns off. So I've got that 0.1 microfarad capacitor back in there with our 1 meg resistor. I think that's what I'm going to go with. And just like before, we've got that control voltage pin, which is pin 5 here that we're not using, and that's just kind of tied into here. And again, the datasheet recommends putting a 0.01 microfarad capacitor between that and ground. So I'll go ahead and add that in there, and that's just for that noise reduction.
Okay, I'm just going to install that.
We saw in the last video, so good practice, put it there. And then the other good practice is pin 4, also not using that. That's a reset pin that kind of ties right into the reset of the SR latch, and it's an inverted reset, so normally it should be at 5 volts, and then bringing it to 0 volts forces this to reset regardless of what's going on over here, just kind of override things. So we'll tie that to 5 volts there, just to prevent that from accidentally tripping or anything like that. And I think that'll...
Cool. So let's just do those 2 things. Pin 5, ground. Okay, and then pin 4. Okay. Alright, so now I think we are actually done, and we have the same thing as him.
We'll do it. So now we've got our timer here, so we've got that, and we can adjust the speed. So we saw that in the last video, and go really fast or really slow. And if we don't want to use that, we've got a manual clock pulse here. So now we just need to come up with some way to switch between the two of those, and we'll look at that in the next video.
I have an entire PCB factory on my bench. I can make perfect PCBs with my fiber laser, and I can populate entire panels in minutes with my Lumen PNP, and then reflow them with my reflow oven. Wait. But what about paste? For rapid prototyping boards, I tried making stencils and it sucked. I tried using a bunch of materials and looked into a different type of laser, but it just sucked. What if I didn't need a stencil? I already made this paste extruder head for the Lumen PNP, and we've already done some really cool stuff with it, but it wasn't easy to put paste onto PCBs automatically until today. I built a Gerber processing, G-code generating, machine vision implemented website that does the whole thing. The Chrome tab itself connects to the Lumen and performs an entire pasting job automatically with machine vision fiducial calibration. It's so cool. So many people have been using our paste extruder, weird, interesting things that NDAs keep me from talking about, but a lot of people have been asking us for an easier way to just drop a PCB in and have it paste the board for you. And this process is only really easy and useful if you have automatic alignment. Every time you mount a board to the machine, it might sit just a little bit different, and manually realigning it stinks. So for this tool to actually be useful, it has to be able to automatically find the exact position of the board every time, which comes with fiducials. Fiducials, the little dots on a PCB that help the camera find out where the board is in space so all the placements are really accurate. If I can find a way to get this web tool to use the fiducials of the board to do the alignment, that's great. So this tool literally runs OpenCV running in WebAssembly. So an entire bundled version of OpenCV is running in this Chrome tab, processing the image that comes in from your webcam, finds the circular fiducial, and can do the calibration based on it. So this uses all the exact same hardware in the original paste extruder I made in the video.
That is so fucking cool,
I'm using a slightly
man.
different nozzle tip here to get a little bit more precise dispensing. These are lure lock tips which are ubiquitous and you can get them anywhere, and they work in the syringes that came with the kit. But aside from that, it's same stock everything. I have the web tool loaded up here and I'm connected to my Lumen. Already the tool is looking and sees all the cameras I have attached to my laptop, and it will by default.
All right, I get the idea. That's very cool.
So in the last two videos, we used these 555 timers to build an astable circuit with the pulsing output, and a monostable circuit that's normally off, but when we push the button, it turns on and it's debounced so that we get a single clean output when we push the button. So this we can use for our clock, and then we can also use for a manual pulse. Now what we need to do is figure out a way to switch between the two. And so you might think, well, we should use a switch. And I've got a pretty good switch here. This is a little push button switch, and it's either out or in, and it's got these 3 leads. And so there's a center common pin, and then it's connected to either this pin or this pin, depending on whether it's in or out. And there's 2, so that's double throw, it's called, and then it's double pull as well. There's sort of 2 sets that are independent. They're just connected to the same button. So double pull as well. There's sort of 2 sets that are independent. They're just depending on whether it's in or out. And there's 2, so that's double throw, it's called, and then it's double pull as well. There's sort of 2 sets that are independent. They're just connected to the same button. So double pull, double throw, and it's a fairly common type of switch. This is another switch here that's the same thing, and you've got the 2 sets of 3 connections there. Of course, this doesn't plug into my breadboard. And annoyingly, neither does this. This is actually just a little bit this pin spacing is a little bit too close together to fit into the breadboard. And so what I've done is gone ahead and soldered these little header pins to the switch. And so that fits in very nicely into the breadboard. And so one thing we could do is we could just connect the output of this here. Well, that's not the output. Let's connect the output of that to one side of the switch. And we could connect the output of our manual trigger over here to the other side of the switch. And then we could look at the middle of the switch, connect that to an LED, and then of course our current limiting resistor here. And we see that it's pulsing. And then we could flip the switch here, and now it's connected to our manual clock pulse. And we can flip it back, and it's connected to the
why is that?
sort of
Why not just do that?
clock pulse there. So this is great. We could use this. This will work. One problem with it is, again, we have a switch in here that's not debounced, and so we could have some situation where maybe we have a really slow clock pulse, and we're going step by step by step, and we're watching our computer execute. Maybe we're troubleshooting some problem, and we're watching it go step by step.
Oh, wow,
we see the problem that we're trying to catch developing.
Yeah, that could work. That could happen. I could see that.
To stop the computer, and so we can figure out what's
So we
going
need
on.
another
Well, if we push
debouncer.
that, we have that debouncing problem, and we get a couple extra clock pulses in there when we were going so slow to catch that one point that we're trying to catch. That could be really frustrating. So we really should find a way to debounce this switch. And you could build exactly this circuit, and that would work fine. I'm going to show you a different way to use the 555, just for fun, just to see yet another use for the 555. And so for this next circuit, what we're going to do is we're basically going to take advantage of the fact that the 555 timer has an SR latch built into it. And we're really only going to use the SR latch. We're just going to kind of try to ignore the rest of the stuff as much as we can. And what we're going to do is we're going to basically hook this switch up to, imagine we could somehow get rid of all this stuff and just hook the switch up to the S and the R. So in one state it's setting, and in the other state it's resetting. And then we have our output. The SR latch will actually act as a debouncer. And one of the reasons it'll do that is kind of a property of these switches, which is, if we look at the switch, if I just hook up a couple LEDs so we can kind of examine how the switch normally works, what you'll see is that it switches between the 2 states when we push the switch, which is what you'd expect. But if we push it very gently, you see it actually, that you can kind of get it in between, and it turns off. And that's actually a pretty useful property. So it's called break before make. And you can buy switches that are make before break if that's what you want. But I think most switches are typically break before make. And so what that means is that, it can be, if this is, say, our reset or our set condition, let's say we're putting a set into this SR latch. Forget the fact that it's part of 555. Just imagine we're looking at an SR latch. If we're setting it, and then we start to push this switch, as we let go, or not as we let go, as we push the switch gently, we're kind of in this middle region. Our latch is still going to be set, right? And then as we continue to push the switch down, we get into the reset. then that reset comes on. Well, if there's any bouncing in the switch, it doesn't matter, because as soon as that first reset happens, the latch is reset, and our output is going to be off. And then the same thing, as we push this and then as we gently let go, the reset goes off. We're still reset, right, because we haven't set it yet. And then even if there's some bouncing as we go into the set state, doesn't matter, because as soon as it first sees that set state, boom, the output comes on. So we can use an SR latch as a debouncer with a switch like this. So the question is, if we're using a 555, well, we could use just an SR latch on its own, in which I've got a video that shows how to build one. But we can use the 555 timer. We can use its SR latch.
I didn't get that. I didn't get that.
The reset goes off as we push the switch gently. We're kind of in this middle region. Our latch is still going to be set, right? And then as we continue to push the switch down, we get into the reset. Then that reset comes on. Well, if there's any bouncing in the switch, it doesn't matter, because as soon as that first reset happens, the latch is reset, and our output is going to be off. And then the same thing, as we push this and then as we gently let go, the reset goes off. We're still reset, right, because we haven't set it yet. And then even if there's some bouncing as we go into the set state, it doesn't matter, because as soon as it first sees that set state, boom, the output comes on. So we can use an SR latch as a debouncer with a switch like this. So the question is, if we're using a 555, well, we could use just an SR latch on its own, in which I've got a video that shows how to build one. But we can use the 555 timer. We can use its SR latch by still using the trigger, right? So remember, we've got 5 volts up here, right? And then we've got this voltage divider network. So this gives us 3.33 volts here and 1.6667 volts here, and of course 0 volts down here. And so if this trigger goes below 1.6 volts, then that sets the latch. And then if the threshold goes above 3.3 volts, that resets it. But we're actually going to ignore the threshold. We're going to just tie this to ground. And so this will never do anything. Instead, we're going to use pin 4, which we haven't used yet on the 555, and that's this reset pin. And it's not wired exactly like this in here, but you can kind of imagine it. But this just gives you kind of a shortcut to the reset. And so if we pull pin 4 low, because it's inverted, that resets it. And if we pull the trigger low, below 1.6 volts, that will turn this comparator on and set it. And so that gives us a way to kind of get into this SR latch. And so what we can do is we can hook our switch up, sort of draw the switch down here. And so we can hook our switch to ground.
If threshold is grounded, then this is, okay.
Connection of our switch to ground, and we hook one side up over to our reset, and hook the other side over to our trigger. And then if we flip our switch over to this side, that'll ground the trigger, which takes this now below 1.6 volts. We should probably have a little pull-up resistor here of some sort. Maybe a 1K resistor will do. So that normally, this is going to be 5 volts, so it'll be well above our 1.6 volts, and so this will be off, and so we won't be setting it. But then when we flip our switch here, and this goes to ground, that'll pull this down to 0 volts, and 0 volts, of course, is below 1.6 volts, and so that'll set the flip-flop, and the output will turn on. And then when we flip our switch over to the other side, we do that break before make, which this diagram actually shows pretty well. When we break, no big deal. We're not setting it anymore, but it's a latch, so the output stays set. But then when we first make contact over here, even if it bounces, doesn't matter. The first time we make contact over here, we reset the latch, and then the output turns off. And so we have this nice debouncing that we can use. So let's hook that up. Okay, here it is. So we got our switch here, and the center pin is connected to ground, which is what we wanted here. And the other two pins, one is connected over here, you can see, to pin 2, and the other one's connected to pin 4. And so just like we've got here, so one's connected over here to pin 2, that's our trigger, and the other one's connected over here to pin 4. And,
okay, so I need to go find the switch. I don't know where my switches are. Okay, give me a sec. It's Anand's law of electronics. Any project, no matter how small, you will end up bringing every tool you own outside. Alright, that's okay though. I just need to solder something really quickly. Let's just get this thing on. Okay. You're just going to... And I just bought some suitable slide switches for breadboards, but for right now... I'm not going to do that. Actually, we probably want the one here. Okay, but before I do that, actually... You know, it's kind of annoying that I keep meaning to design something that will let me change the zoom without it being annoying on me. But this should work just fine. Probably can't see that, that's fine. Also later today, I think I got this carbon filter, and I saw Great Scott built this fun fume thing. Alright, that's that. You know, sometimes this stuff is plated in a way that you, it doesn't work very well, but alright, so we have our switch now. So we can get started building this thing. So we're at 26. This thing is going to start at 26. And go to 28. Okay. Oh, and let's do this. Okay. Now we have our selector. Wait, actually, this isn't gonna work. I needed a double throw. I didn't even realize that. Dope. Okay, I need a double throw. Okay, let me go look for a double throw. Okay, well luckily I found one with leads already on it. So that's nice. So that was a waste of time. So how does this work? Yeah, so we need this to be like... So first off, let's just... I think I know what this means, but let me just check with a multimeter. Yeah, it's so annoying that I can't lock the zoom. Okay, well, whatever. Let me just do this. Okay, so I'm just testing that this thing operates like I expect it to. God, this thing is so fucked. This one's pretty good, though. Okay, so it's connected. Wait, what? But then here... Okay, good. So we should be able to just jam this in 26, 27, 28. Alright, cool. It's not the prettiest, but it will work. That's what matters. Is will it work? Alright, so let's get back to it. Okay, so now it's just a bunch of wiring. Okay, so the first thing we need is another 555. Okay, so I have this little box of integrated circuits with a whole bunch of 555s. Okay, and then the 555 goes at position 30. Okay, then we're gonna ground. Okay, so the center is grounded. Now this first one is going to pin 4 because this is that assertion pin. Okay, so we want to go to there, so then I'm going to cut right here. I'm going to cut 2 after. He said to cut 1 after, or 3 after, but I'm not down with that. I think that's too much. So then what I'm going to do is I'm going to squish it where I plan to break the insulation. Then I'm going to take it out. Okay. Fold it. Let's see, did I do it right? Yes, I did. That looks great. The thing about these electronics is they are so freaking slow to make, man. But I feel like when you get in the groove, it's not so bad, but it is just dang slow. So then the second one here is going to pin 2, because what is it that we want to do? We want to
So in the last 2 videos, we used these used the SR.
So pin 2 has a 1K resistor to high. So pin 2 is going to have a 1K resistor to high. Oh yeah, which gets pulled low by this. Okay, so then we're going to go to pin 2. Then you know 1, 2. We're going to cut it right here. Okay, then we'll grab it. And strip and fold. Okay. Now we just need a 1K resistor, which we most certainly have, thanks to my new box that I found. I like the resistor kits that give you more of the more common ones. It's like, I don't need 50 like 9.1Ks. I need like, you know, I don't know. Some values are just more common than others. Okay, so pin 2 is getting tied to high because what happens is when we switch this switch on, pin 2, which is the trigger, is going to go low, which means that we're setting it. So this is setting this. Okay. Then pin 4 also has a 1K. Why does it look like pin 4 has a 1K?
Debouncing that we can use. So let's hook that up. Okay, here it is. So we got our switch here, and the center pin is connected to ground, which is what we wanted here. And the other 2 pins, one is connected over here, you can see, to pin 2, and the other one's connected to pin 4. And so just like we've got here, so one's connected over here to pin 2, that's our trigger, and the other one's connected over here to pin 4. And On both of those I have pull-up resistors. So you can see on pin 2 and pin 4, I've got a resistor going to 5
Okay,
volts.
so we actually need another one. Cool. Pull up on 4.
Draw that over here, but you know, we want to make sure that these are normally getting 5 volts unless our switch is set. Pin 3, of course, is our output, so I just have that going to this LED for now with a current limiting, 220 ohm resistor over there, and then
Okay. See, this has all the values that you want. That's the cool part about this thing. You got what I need. You say he's just a friend. You say he's just a friend. Oh, baby, you got what I need. Bismarck key, bro. Damn it. These things fucking bother me. There we go. Get in there. Okay. So we're sort of getting there. We just need to give this thing power and ground. So let's do ground. First, let's put this resistor away. Okay. Now let's get the voltage. power up. Okay, we got the power. What's next? So pin 6. So wait, I keep forgetting the pinouts. We need to just keep going back to the pinouts because I keep forgetting what they are. So pin 5, I forget in the block diagram where that's supposed to go though. Oh, pin 5. Yeah, pin 5 just gets capped to ground because it's the negative side of the first comparator. But pin 6, hold on, we need to watch the operation part of this video again because I'm building this and I don't even remember what's going on here.
Well, there's sort of two sets that are independent. They're just connected to the same button. So double pull, double throw, and that's a fairly common type of switch. This is another switch here that's the same thing, and you've got the two sets of 3 connections there. Of course, this doesn't plug into my breadboard. And annoyingly, neither does this. This is actually just a little bit this pin spacing is a little bit too close together to fit into the breadboard. And so what I've done is gone ahead and soldered these little header pins to the switch. And so that fits in very nicely into the breadboard. And so one thing we could do is we could just connect the output of computer execute. Maybe we're troubleshooting some problem and we're watching it go. I'm going to show you a different way to use the 555 just for fun, just to see yet another use for the 555. And so for this next circuit, what we're going to do is we're basically going to take advantage of the fact that the 555 timer has an SR latch built into it. And we're really only going to use the SR latch. We're just going to kind of try to ignore the rest of the stuff as much as we can. And what we're going to do is we're going to, basically hook this switch up to.
So we have a way to set the trigger low, and we have a way to set the reset low. And then the threshold. The threshold is low, so this is always low. So then it's only that, right? That's what he's saying.
We're going to, basically hook this switch up to, imagine we could somehow get rid of all this stuff and just hook the switch up to the S and the R. So in one state it's setting, and in the other state it's resetting, and then we have our output. The SR latch will actually act as a debouncer. And one of the reasons it'll do that is kind of a property of these switches, which is, if we look at the switch, if I just hook up a couple LEDs so we can kind of examine how the switch normally works, what you'll see is that it switches between the two states when we push the switch, which is what you'd expect. But if we push it very gently, you see it actually, you can kind of get it in between, and it turns off. And that's actually a pretty useful property. So it's called break before make. And you can buy switches that are make before break if that's what you want. But I think most switches are typically break before make. And so what that means is that it can be, if this is, say, our reset or our set condition, let's say we're putting a set into this SR latch. Forget the fact that it's part of 555. Just imagine we're looking at an SR latch. If we're setting it and then we start to push this switch, as we let go, or not as we let go, as we push the switch gently, we're kind of in this middle region. Our latch is still going to be set, right? And then as we continue to push the switch down, we get into the reset. Then that reset comes on. Well, if there's any bouncing in the switch, it doesn't matter, because as soon as that first reset happens, the latch is reset, and our output is going to be off.
It's not going to bounce
and then the same
all
thing
the
as
way
we
back.
push this, and then as we gently let go, the reset goes off. We're still reset, right? Because we haven't set it yet. And then even if there's some bouncing as we go into the set state, doesn't matter, because as soon as it first sees that set state, boom, the output comes on. So we can use an SR latch as a debouncer with a switch like this. So the question is, if we're using a 555, well, we could use just an SR latch on its own, which I've got a video that shows how to build one. But we can use the 555 timer. We can use its SR latch by essentially using the trigger, right? So remember, we've got 5 volts up here, right? And then we've got this voltage divider network. So this gives us 3.33 volts here and 1.6667 volts here, and of course 0 volts down here. And so if this trigger goes below 1.6 volts, then that sets the latch. And then if the threshold goes above 3.3 volts, that resets it. But we're actually going to ignore the threshold. We're going to just tie this to ground. And so this will never do anything. Instead, we're going to use pin 4, which we haven't used yet on the 555, and that's this reset pin. And it's not wired exactly like this in here, but you can kind of imagine it. But this just gives you kind of a shortcut. Here, and the center pin is connected to ground, which is what we wanted here. And the other 2 pins, one is connected over here, you can see, to pin 2, and the other one's connected to pin 4. And so just like we've got here, so one's connected over here to pin 2, that's our trigger, and the other one's connected over here to pin 4. And on both of those I have pull-up resistors. So you can see on pin 2 and pin 4, I've got a resistor going to 5 volts. I didn't draw that over here, but we want to make sure that these are normally getting 5 volts unless our switch is set. Pin 3, of course, is our output, so I just have that going to this LED for now with a current limiting 220 ohm resistor over there. And then pin 6 is our threshold, so we have that just at ground, so this comparator is never going to be on, so we don't have this resetting this way. The only way we're resetting the latch is through our reset pin. So threshold is to ground, and then pin 7 is our discharge pin. No need to connect that. We're not discharging anything. There's no capacitor in here. So we just leave that disconnected. And then pin 5, as usual, we have our 0.01 microfarad
falling apart.
Oh, it's gonna be brutally low.